You have probably heard of string theory, an attractive development in theoretical physics which has run wild through the scientific community and media alike. It has seen so much attention due to its incredible answers to deep questions of fundamental physics, to the extent that some consider it a candidate for a theory of everything. String theory itself is not exactly a theory, but more a type of theory called a theoretical framework, through which there are multiple different versions of the same base principle. String theory's base principle is that all the points of particle physics, like leptons or quarks, are replaced by one-dimensional strings, which are on the scale of the Planck length, and are either open or closed. These strings vibrate, and the way they vibrate determines which particle they look like at a larger scale. But for the maths to support various string theories, we need more dimensions. At the moment, we are very happy with our 3 spatial and 1 time dimension, but string theorists imagine that there could be many more. Bosonic string theory, for instance, theorizes that there are 27, yes, 27 different dimensions to our universe. The reason that we don't notice these extra dimensions is because they're curled up incredibly small. Imagine you have a pole on which a tiny object can move. Close up, you can easily see how the object can move not only up and down the pole, but around the circumference as well, and the object itself would only be able to comprehend these 2 dimensions. However, if you step back far enough, you will only be able to notice 1 dimension of movement, up and down. This is the essence of extra-dimensional space, or hyperspace. String theories allow quantum gravity to be explained, something that very few quantum theories have been able to do. Gravity, as understood by Einstein's general theory of relativity, often has serious disagreements with quantum physics. One main reason for this is that gravity, describing the geometry of space-time itself, requires precise measurements of distance, and at the quantum level, these properties cannot be measured precisely enough due to the Heisenberg uncertainty principle. The brilliance of string theory is that it introduces gravitons, particles that mediate gravity, allowing gravitational interactions to be explained in quantum physics. This was what caused some to name string theory a potential theory of everything, despite others criticizing it for its unfalsifiability. Well, what makes a theory of everything? A theory of everything, in the most basic sense, is a theory that encompasses, well, everything of modern physics. This seems like a great deal of work, but thankfully a lot of it has already been done. We in fact have a single model, humbly called the Standard Model, that describes almost all of the known universe, excluding 1 or 2 final stepping stones. The biggest of these final pieces is gravity, and a clear signpost that you have a theory of everything on your hands is if it connects gravity to the Standard Model. As we know, general relativity, Einstein's theory of gravity, really dislikes quantum theories, but there is another very promising scientific principle called supersymmetry that could help us combine gravity and quantum physics. Supersymmetry is the principle of treating forces and matter equally, and predicts cousin particles for every elementary particle we've observed, called superpartners. These superpartners are of the opposite class to their regular versions. For instance, electrons, supersymmetric partners of the electron, are bosons, where electrons are fermions. A supersymmetric theory would have its force equations identical to matter equations, and for this reason many physicists are attracted to the way supersymmetry relates force to matter, bosons to fermions, making the Standard Model more elegant. Physicists already appreciate the symmetry in particle physics, between the 6 quarks and antiquarks, and between the 6 leptons and antileptons, and can see the mathematical significance of this symmetry. On the other hand, many criticize supersymmetry on the grounds that no superpartner particles have been observed, and to test the principle, it would take a gargantuan-sized particle accelerator, capable of collisions up to 7 million times more energetic than the LHCs. Nonetheless, supersymmetry, when combined with general relativity, results in very elegant and satisfactory solutions, and this is called supergravity. Supersymmetry can also be applied to string theory, and this gave rise to 5 superstring theories, each with 10 total dimensions. These superstring theories individually explain a number of questions in quantum physics, and do so extremely well. However, these superstring theories were found to be perturbative, with no single one seeming to be a theory of everything, and it looked like string theory had failed to reveal the nature of our universe. That was until an American physicist named Edward Witten noticed that the 5 string theories could be mapped to one another by certain conditions known as dualities. Then, in a string theory conference at the University of Southern California in 1995, he suggested that instead of these string theories being distinct theories, they could in fact be cornerstones of a more fundamental theory called M-theory. This started a huge amount of work, which became known as the second superstring revolution. M-theory could be defined as a proposal for a unified quantum theory of the fundamental constituents and forces of nature, which contains within it the 5 superstring theories and supergravity. It has since been considered the best candidate we have for a theory of everything by the likes of Stephen Hawking and Michio Kaku, but the M in M-theory might as well stand for mystery or miracle, because no one really knows very much about M-theory at all, even its name. M-theory could be a single theory, or a network of different theories. In either case, we are already aware of some of its base principles. Firstly, M-theory is 11-dimensional, and it contains not just one-dimensional strings, but other fundamental objects with a range of different dimensions, called p-branes, where p runs from 0 to 9. This includes 0-dimensional points, membranes which are 2-dimensional sheets, 3-dimensional blobs, 4-dimensional hyperblobs, and so forth up to 9 branes, which are pretty difficult to imagine. The 11 dimensions of M-theory contain our familiar 3 macro dimensions and time dimension, but what about the remaining 7 tiny dimensions? These extra dimensions must be either curled up or at right angles somehow, otherwise they would cease to be tiny dimensions. And the maths of M-theory restricts the number of ways the internal space can be shaped as such. We know that the shape of internal space directly affects the values of physical constants, such as the charge of the proton and the way elementary particles interact. In this way, the shape of internal space determines the laws of nature less fundamental than those of M-theory, like the laws of chemistry. We can say, therefore, that whilst our universe has a certain way of shaping hyperspace and so certain laws of nature, the laws of M-theory allow for other universes with different ways of shaping hyperspace, and so vastly different laws of nature. How different? 10 to the 500 different, according to M-theory's mathematics. This means that M-theory allows for 10 to the 500 different universes, and 10 to the 500 is a very large number. This multiverse possibility is just another way M-theory has caught the attention of so many. But is M-theory the grand unified theory we have been looking for? For that, we will have to wait and see. But should it be confirmed by observational evidence, we will have made huge progress in understanding our universe.